So now magnetic force between two wires. You already have enough information to solve problems like these, but there's a bit of a shortcut. That is, there's an equation that you could use. So suppose that you have a wire that points like this, another wire that points like this, and then you have, let's set up a current in each one. So let's say that the current flows like this. Here's I1, and then here's I2. Whether the currents flow in the same directions or opposite directions, you can calculate the same. It doesn't matter as far as calculating the magnitude of the force is concerned. What it will determine, though, is in which direction the force will act on the wires. But anyways, first let's consider this case, and then we'll come back to the other case where you have I1 flowing like this, and then I2 flowing in the opposite direction. So we'll come back to this case. For the moment, let's consider this. So what we have here is I2 is going to set up a magnetic field at the location of I1. Right, you would use the right hand rule, the one where you curl your fingers. So take the thumb of your right hand, point it in the direction of this current I, and then curl your fingers, and you will see that the magnetic field here points like this. Of course, the farther out you move, the bigger the circle, if you will, that you would have to draw, but there's going to be a magnetic field there until eventually you move out far enough so that you're at the location of this wire here, and then you have this magnetic field that points out of the page and does something like this, and then here out of the page does something like this, here out of the page and does something like this. Let's get rid of all of these circles and just indicate with dots that we have the magnetic field pointing out of the page at the location of this wire here. So that, and that magnetic field due to B2 points out of the page, and note that that magnetic field is due to I2, and so I'm going to draw this arrow here. That field is set up by this current, and it is this magnetic field is set up at the location of this wire. And so now what I have is a force that acts on this wire. So I can write that the force on the first wire on top is going to be I1 times the length of this wire times the magnetic field present there, which is B2. Right, and so now, but the equation for the magnetic field due to a straight wire is just going to be mu naught times I over 2 pi r. And now this is B2 due to I2, and this r is the distance from where the current is to the point of interest. Remember, you're looking at this circle here, and there is the r of that circle. That's this r. All right, now that we have this, we can continue on. Let's just combine the two equations. So what I have is I1 times L times mu naught times I2 divided by 2 pi r, and you can rearrange this into mu naught times L times I1 times I2, all of it divided by 2 pi r. This is the equation for the force between the two wires that carry current. So if you have a wire here, current flows like that. You have a wire here, the current flows like that. Here's I1, here's I2. If you know the distance between the two wires, which is just r, then you're all set. Well, you still have to know the length of the wire, so I guess I'll add that to this picture here. Here. Know the length of the wire. And you can then calculate the force between the two wires. Now, whether the currents flow in the same direction, opposite directions, makes no difference. It's the same equation. This equation still gives you the magnitude. The difference is in the direction, though. So let's figure out the direction of the force in this specific case. Let's go back to this picture. Let's figure out the direction of the force, magnetic force. So use the right hand right here, right hand rule. By using the right hand rule, you can figure this out. So I'll walk you through it. take your right hand, align the fingers of your right hand to come out of the screen towards your face. Rotate your thumb in such a way that it points in the direction of the current. If you do that, the fingers of your right hand are pointing at your face and the thumb is pointing in the direction of current I1. If you do that, then you will see that the force as it comes out of the palm of your hand points down the screen. So the force here on this wire just points like this. This is the force F. And the magnitude of this force is this. This is how you calculate the magnitude of that force. But note that this force points towards the other wire, therefore this would be the attractive force. So if you have the two wires that point in the same direction, you end up with an attractive force. F is attractive. Now, let's analyze this picture though, and you can probably guess that this force is going to be repulsive, but let's just figure this out. Let's see if that's in fact true. So let's take this current, points to the left, take your right hand, take the thumb of your right hand, make it point in the direction of this current, and then take your fingers, curl them, and determine the direction of the magnetic field. The direction of the magnetic field set up by I2 is going to be this. Right? And if you were to move out a little farther, you would see that you would still get a circular magnetic field. It's just that now it would point like this. And if you were to move a little farther, you would finally end up with a magnetic field that reaches current 1. And so you'd have the magnetic field that does something like this and points into the page on the top. And here it does something like this and points into the page on the top. And then this one does something like this and it points into the page on the top. So I don't need all of these circles. I'm going to get rid of them. And the magnetic field here on the top just points into the page. So I'm going to indicate this with X's. This is B2 because it is due to I2. All right, now that I have this magnetic field here and I have the current, I can determine the direction of the force. So using the right-hand rule, I'll walk you through this again, see if you can follow what I say, but take your right hand, make the fingers of your right hand point into the screen. Then rotate your right hand such that the thumb points in the direction of the current I1. At that point, you will see that the force comes out of the palm of your hand and it points up the screen. So force here is going to point up screen. This is the force. And that should be clear enough that in that case, this force, the force between these two wires is repulsive. And so I'm going to add this to the bottom here. Suppose that this one points in this direction. This is I1, but instead I2 points in the opposite direction. You can figure out the force. The force is going to be repulsive. So the force will point like this on this wire. It will point like this on this wire. F is repulsive. But you can calculate it. This is distance R, distance between two wires. But you can calculate it using the same equation. So it's the same equation for both repulsive and attractive force. But in one case you have attractive force, and in the other case you have repulsive force. Okay, so there's your force between two wires. So here's a sample problem. These problems are not very difficult. Suppose you have a wire that points like this. Suppose you have a wire that points like this. Here's I1. Say this is 10 amps. Here's I2. Say this is 12 amps. And the distance between the two wires R is 10 centimeters, so 0.1 of a meter. And what else do I need? I need the length of these two wires. So let's say that they both have a length of 30 centimeters, so 0.3 of a meter. All right, let's calculate the force. So the unknown is the force between the two wires. Well, that's fairly easy to do. F equals mu naught times L times I1 times I2 divided by 2 pi r, and this will give me, let's plug in whatever we have. So this is mu naught, length is 0.3, 0.3, times the two currents. So I have 10 times 12, all of this divided by 2 pi times the distance between them, which is just 1/10, so 0.1. Pi goes away. 2 and 4, that's 2, and then I have 1, so that's 10, so this gives me 100. I'm just gonna use a calculator. So equals, let's see what we get out of it. So 7.2 times 10 to the minus 5th newtons. And that's it. So I still have to say whether this force is attractive or repulsive. And it's clear enough that I have this being the case, the two currents flow in opposite directions, and so the force is repulsive. And that's it. Two wires carrying a current will exert a force on each other. Sometimes attractive, sometimes repulsive, depending on the directions.